Good afternoon, everyone. I'm Xiaohu from Tsinghua University. It's my pleasure to present our paper, Fog in the Load, Reflection and Optimization for Cold Start Latency in Production Serverless System. This work is a collaboration between Ant Group, Tsinghua University, Shanghai Jiao University, and the Zhengyu Librarian. Serverless computing has many benefits, such as on-demand scaling, pay-as-you-go pricing, and the ability for developers to focus on code without worrying about infrastructure management. It has wide adoption in many public and private clouds. However, cold start remains a critical problem. Our analysis of Ant Group's public cloud trace reveals that over 95% of requests are cold starts, but they cover just a small set of frequent functions. The remaining 5% invocations include major functions across the platform. Specifically, 7% of all functions experience more cold starts than hot starts, and 35% of all functions always experience cold starts. Furthermore, we found that 18% of requests are short functions that finish execution within just 221 milliseconds, demanding extreme cold start performance. Serverless research has made great progress to improve cold start in the past several years. Some work even makes the initialized latency lower than just 1 millisecond. So how far did we go? Is the progress of the current serverless research enough for making efficient practical serverless system? No, there is still a large gap between them. For example, we have deployed the SOTA serverless system catalyzer in Ant Group. Catalyzer is a security container that offers 7 milliseconds startup time with a sandbox fork. It also has a good compatibility and does not need specialized hardware. However, even though Catalyzer can achieve great container stop latency, it is still inefficient for optimal performance in the real world. First, Catalyzer is inefficient for end-to-end latency. Apart from container initialization and execution latency, we observe a 32.8 millisecond gap, which is a meaningful cost. Second, although container initialization latency has been successfully optimized to a very low level, the performance is not stable. We observe noticeable tail latency. As shown in the figure, the tail latency tends to increase as concurrence levels go up. Third, Catalyzer experience a big drop in the throughput and sustained high concurrency. For example, during a 1-hour load test with 4 concurrence, the throughput gradually dropped from 110 functions per second to 74 functions per second by the end. So the figure shows the cold start procedure, which includes the main phases. First, the control path phase. The high-level container runtime, such as container D, will issue create commands to low-level container runtime, such as Catalyzer, to start a new instance. Second, the container initialization phase. Catalyzer forks a new instance from a prepared set. New instance load and initialize the user code and dependency. We identify 3 key gaps in each phase. First is control path latency. It involves hurry multiple component interactions, which takes about 80 milliseconds, but have been overlooked by previous work. Second, resource contention latency. Although content initialization latency has been heavily optimized down to millisecond levels. It was not stable at scale due to resource contention. Set use code initialization latency. It depends on user-specific behaviors. Current solution has to trade cost for efficiency. We build AFAS, short for interface, based on catalyzer, and propose 3 new designs to adjust these gaps. First, next I will explain each gap and how AFAS adjusts them in detail. For gap 1, the OCI specification that defines the industry standards content architecture. Its module design in control bus offer extensibility, but not efficiency for performance critical scenarios such as serverless. As shown in the picture, each operation will redirect to a Shen process and then need to load the catalyzer binary to invoke the sandbox. The long and heavy interactions bring significant cost. To fill the gap, we propose a new specification, function runtime interface, to shorten the control path. Function runtime interface include a plug-in design and can interact with AFAS directly. By reducing minimal modularity, AFAS is able to unlock significant performance in control bus. For gap 2, we profile and analyze the tail latency in each step. In the closest core can increase from 1.5 millisecond to 418 in worst case scenarios. The reason is that the creation of new network and IPC namespace may result in contention for host kernel locks. And during the network preparation phase steps, it exhibits substantial latency degradation from 2 milliseconds to 12.2 milliseconds because this phase involves kernel resource operations such as config JSON path and ZNS netlink, such as involves many clock, such as task lock. And the network stack initialization and the seccomp installation also experience longer tail latency due to the construction of complex kernel data structure and the BPF just-in-time compiler. We also found that IPC namespace creation depends on the allocation of super blocks. Performance will degrade in long-lasting and high concurrence situation when the super block cache capacity is empty. To reduce resource contention latency, we designed to fork-friendly optimization, pooling, and sharing for resources that can be pre-allocated, such as C group and virtual ASNIC. We use a pooling strategy to allocate them in advance and reducing concurrence conflicts for inheritable and shareable resources. We integrate them into a set to avoid the new resource allocation. Through these new strategies, AFAS can retain the low latency performance of sandbox fork in high concurrence scenarios. For gap 3, user code initialization involves loading the language runtime, framework, dependence, and user code. These processes are time-consuming and impacts cold start latency a lot. Including user code in the seed is a possible solution. However, due to the variety of user code, creating a single set for each one requires significant memory. This makes deployment difficult in production environments. AFAS uses chain structure seeds and a multi-level fork mechanism to balance performance and resource usage. Function seeds are organized in a tree. When need to fork an instance, AFAS sets the tree bottom to up to find the best fit sets. This design has two advantages. First, it can reduce global resource consumption through copy on write. And second, it provides best effect performance, even though without user code specific sets, a function can still use language runtime set or the load WIM set. We compare AFAS with an enhanced classer, and we call cut only in this context. We also include the divisor and cutter as the baseline because they are production ready and open source and can support the same hardware configuration. So we use functions from function bench and real productions for evaluation. First, we test the AFAS end-to-end latency serially. Results show AFAS significant outperform classer for short-lived functions by 3.8 to 31 times. When the execution is long, the advantages are not that high. We also test AFAS tail latency and high concurrence and saturation load. AFAS achieves the lowest tail latency, and it shows no performance degradation even after 1 hour of continuous high concurrence. Later, we also test past steps tail latency. It can be said that the tail latency of each step after optimization have reduced. More interesting, the tail latency of unoptimized phase has gone down too because of the global contention is mitigated. AFAS achieves highest scalability and the lowest end-to-end latency at any scale. In memory usage tests, when the size of the use code was small, AFAS the chain structure sets can reduce memory usage by 8 to 18.5% compared to the cut only. When the use code is large, the benefit is less noticeable. We compare the performance of AFAS with the cut only in production environment. AFAS achieves 1.8 and 8.1 speed up with stable code start latency of 5.45 and 9.4 milliseconds. AFAS has run stably in and groups public and private clouds for over 18 months, supporting diversity workload, including short-lived functions, microservice, AI, and big data analytics. We conclude to experience to build the AFAS. First, Feng has the great potential in building high-performance, stable, and efficient system. Second, Feng-based approach of advantages. There are still some unexpected issues that could be beneficial to know advance. First, the new forked instance may inherit unwanted status from the seed. It is necessary to carefully handle to prevent vulnerabilities. Second, it would be better prepare resource pools in sequence to avoid other workloads. And third, bottlenecks still exist in ultra high concurrence. For example, the seed can become a bottleneck as only one instance can be cloned from the same seed process at a time. Finally, we finish conclusion with a paper's title. Its paper witness a fast journey, generally from prototype to production developments, highlighting three critical bottlenecks discovered in practice and proposes three new practical design to make a fast efficient for real and large deployments. We have also open source cold start trace datasets in and Globe's public cloud and release AFAS as their online service. I hope this will be help to the community. Thank you.